Okay, so this lesson is on the extreme value theorem. And this one, you guys, is truly, truly not rocket science. So here it is in words. If a function is continuous, then f of x has both a maximum and a minimum value. So I'll let that sink in for a second. So all it is saying is that if I draw any piece of a function from a to b, so here's my interval, that this function is going to have a highest point and a lowest point. There exists a maximum and a minimum, is what we should say. That's why these are called the existence theorems, because they prove that certain things exist. Okay, so this interval, we'll call this first point x1, has a minimum at x1, and then a maximum up here at the end point at x2. Okay, that's all there is to it. So what we can do is we can use this to prove that the highest and lowest points of a function are at certain spots. Okay. Now, it's important that there are closed brackets here, and it's important that the function is continuous. Okay. So continuous on a closed interval, this is the hypothesis of the theorem. So what this means is my function cannot be this, discontinuous. The reason for that is like maybe the function has a vertical asymptote where it goes up forever, and this no longer has a maximum, right? The maximum is undefined. So this case is out. The function has to be continuous. And the same if we give, even if we did parentheses instead of brackets, say it was the interval a to b, that means the function doesn't have to touch b, so that means we could have it defined on a and then go up forever at b and have an asymptote at b. Okay, so the closed interval portion is important because it kind of eliminates these two cases where you have an asymptote and the function has no maximum or minimum. But that's all there is to it, is that like if this applies, there's a max and a min. And it's unlikely that they'll give you something like this on the AP exam where you're like, oh, not a closed interval, thus it doesn't apply. I think you need to worry about the continuity piece. Let's look at some delta math problems. Okay, so here's as simple as they get. So selected values of the function f, which is continuous in the closed interval 2 to 10. So that's what we're going to read for. Making sure the function is continuous. Again, that's why we're studying this with the intermediate value theorem, because they have the same hypothesis. And then selected values are shown in the table below, but we just need to know whether f has a maximum value in the closed interval. And the answer is yes, duh. So like if this function is some continuous line, we don't care where it is, but like somewhere there's going to be a maximum, right? So here's my maximum in this case. Okay. That's all there is to it. This obviously does not match the values in the table because this seems to be strictly increasing, but that's okay. So this one would be true. And that's just true because it's the basic formulation of the extreme value theorem. So anytime the function is continuous, if it just asks you if f has a maximum or a minimum, you're like, yeah, duh. Here's another way they can say this. So again, f is continuous. There is a number c in the closed interval from -1 to 8 such that f of c is greater than or equal to f of x for all x. Okay. So that just means that this is a maximum, right? Greater than all the rest of the function means that's a max. Okay, so this is the same as our last example. This is just like a slightly more rigorous way of saying it. Okay, so this is also true by the extreme value theorem. Here's another example. And as you read this one, alarm bells should be ringing a little bit because this says open interval. So for this one, the extreme value theorem does not apply because open interval means the function could have like a vertical asymptote or horizontal asymptote at one of these boundaries. Okay, so here we would say like neither true or false. Okay. So now's a good time to pause. We're about to look at some harder ones, so make sure, check your understanding for the last couple that we looked at. So here's our first slightly trickier one. And here's where we start to really get into the like sort of math logic at play here. So what you should be thinking as you read this is that this is the extreme value theorem in reverse, right? So usually in the past examples we've said like f is continuous, tells us that there's a max and a min. Here the logic is minimum tells us continuous. And we want to know true or false. I think continuous has two u's in it. Okay, so this is not necessarily true. Okay, it's like saying, here's an example. So it is raining, so the sidewalk is wet, versus the sidewalk is wet, so that it is raining. Okay, so the first one is probably true, right? So like the sidewalk always gets wet when it's raining. But sometimes the sidewalk is wet and it's not raining, right? So the sidewalk is wet, so it is raining is not logically true, because like it could be sprinklers. It could be it rained 5 minutes ago but stopped, right? So this is equivalent to minimum, therefore continuous, right? Because I could draw a function. Here's a minimum. Here's a discontinuity, and it keeps going, right? So that is this example. So here we would say not necessarily true. So these existence theorems, you cannot reverse them. They only work in one direction. So if you say that f is continuous, you can prove a max and min, but having a max and min doesn't necessarily mean that the function is continuous. It's kind of a squares and rectangles situation. And then these last couple, we're going to look at in tandem, because they're very, very, very similar, but have different answers. So f is continuous for the first example. And if you're looking at the second example and being like, well, it doesn't say that f is continuous, you're doing a great job. However, and we don't know this fact yet necessarily, this is one of the things we skipped this year because remote is making us slower, but differentiable means also continuous. Differentiable means that the derivative exists, and if the derivative exists, the function is also continuous. So we can use that to know that the extreme value theorem applies. Okay, so the extreme value theorem applies to both of these. The difference, though, this one says the minimum value of f is 2. And on first glance, you're like, yeah, duh, that's the minimum, right? But this graph could look like this, right? So maybe 2 is here, and there's some other minimum down here before it goes up to 5, right? So because we don't know whether the graph is increasing or decreasing and where, we don't actually know that this is true. So this is like a not necessarily type of problem. But where the derivative is given to us, we know. So we know that this is 10, and f prime bigger than 0 means that f is increasing everywhere, right? So we can logically conclude that f is always increasing, and therefore 10 is the true minimum here. So this one is true. So this last distinction is the hardest one. Watch out for these ones where they tell you that f is differentiable. Okay, so there may be some more complicated reasoning at play.